Before the sun dies, it will give us a warning so slow that no human generation would ever notice it. There will be no single morning when people look up and realize the end has arrived. There will be no sudden explosion in the sky, no giant wave of fire sweeping across the solar system in one dramatic second. The truth is stranger than that. The death of the sun begins quietly. It begins while the sun still looks normal. It begins with a tiny increase in brightness, a tiny shift in balance, a tiny change in the amount of energy Earth receives every day. And over deep time, that small change becomes enough to rewrite the future of oceans, continents, weather, life, and eventually the planet itself. Before we begin, if you enjoy calm space documentaries like this, make sure to subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. It is always incredible to imagine people listening from different cities, different countries, and different nights around the world, all looking up at the same universe. Tonight, you are watching the Just About Space channel, talking about what happens when the sun finally dies. And to understand the death of the sun, we first need to understand why it has not died already. The sun feels eternal because it has been here longer than anything human beings have ever known. It was already shining before the first trees. It was already shining before the first animals walked on land. It was already shining before Earth had grass, flowers, birds, mammals, cities, language, memory, or history. Every civilization that has ever existed grew up under the same star. Every ocean wave, every forest, every harvest, every storm, every sunrise, and every shadow on the ground has depended on the same source of light. But the sun is not eternal. It is a star, and stars are not permanent objects. They are temporary arrangements of matter and gravity. They are enormous spheres of gas caught in a long battle between collapse and pressure. Gravity tries to crush the star inward. Heat and radiation from the core push outward. As long as those two forces remain balanced, the star appears stable. From the outside, it looks calm. From Earth, it looks almost unchanged. But deep inside, the sun is burning through a supply of fuel it can never replace. That fuel is hydrogen. At the center of the sun, temperatures reach roughly 15 million degrees Celsius. Pressure is so extreme that hydrogen nuclei are forced close enough to fuse together. Normally, two positively charged nuclei repel each other. They do not want to touch. But in the core of the sun, the weight of the entire star presses inward with such force that hydrogen nuclei can overcome that repulsion. They fuse into helium. A small amount of mass is converted into energy. That energy becomes the sunlight that reaches Earth. Every second, the sun turns hundreds of millions of tons of hydrogen into helium. The number sounds absurd because the sun is absurdly large. It can lose mass in the form of energy every second and still continue shining for billions of years. But the supply is not infinite. The sun began with a huge amount of hydrogen, especially in its core, and over time that core is becoming richer in helium. Helium is heavier. It does not fuse easily at the sun's current core conditions. So as helium builds up, the core slowly changes. This is the first quiet step toward the end. Not a disaster, not yet. Just chemistry and gravity working on a timescale so long that it feels almost motionless. The sun is still in the main sequence, the long, stable chapter of a star's life, when hydrogen fusion in the core provides the outward pressure needed to resist gravity. Our sun has been in this phase for about 4.6 billion years, and it is expected to remain there for roughly another 5 billion years. In human terms, that sounds like forever. In the life of the star, it means the sun is middle-aged. But even during this stable phase, it is not truly constant. As helium accumulates in the core becomes denser. Gravity compresses it. The temperature rises. Fusion in the surrounding hydrogen becomes a little more intense. The sun slowly brightens. It has already become brighter since Earth formed. Billions of years ago, the young sun was dimmer than it is today. Early Earth received less solar energy, and yet somehow liquid water existed on the surface, helped by atmospheric conditions very different from the modern world. In the future, the process continues in the other direction. The sun will grow more luminous, not suddenly, not in a way that tomorrow's sunrise looks different from today's, but over hundreds of millions of years, the increase becomes important. A star does not need to explode to destroy a habitable planet. It only needs to change the balance slightly. Earth survives because it sits in a narrow range where sunlight, atmosphere, oceans, clouds, ice, greenhouse gases, and geological cycles hold the climate in a livable state. Shift that balance enough, and the world begins to move away from the conditions that made life possible. That is what makes the sun's future so unsettling. The end of Earth does not begin when the sun becomes a red giant. It begins much earlier, long before the sun physically reaches toward our planet. Its growing brightness will begin to push Earth out of the comfortable zone it has occupied for billions of years. The first stages of that future would not look like science fiction. They would look like climate slowly losing its ability to recover. Imagine Earth hundreds of millions of years from now. The continents are in different places. Mountain ranges have risen and eroded. Oceans have opened and closed. Species that exist today are gone, replaced by life forms we cannot predict. The night sky still has the moon. The sun still rises. To any creature living then, the world may still seem normal, but the amount of sunlight arriving at the top of the atmosphere is higher than it is now. Weather patterns respond. The water cycle grows more aggressive. More evaporation rises from the oceans. More water vapor enters the atmosphere. Water vapor is a greenhouse gas. That matters because once extra heat causes more water to evaporate, the extra water vapor traps more heat, which causes still more evaporation. This does not mean the oceans instantly boil. The early changes are gradual, but the climate system begins to move toward a dangerous feedback. Earth has survived many climate shifts, ice ages, greenhouse periods, asteroid impacts, volcanic catastrophes, and mass extinctions. But a steadily brightening sun is different. It is not a temporary shock. It is a permanent change in the energy source that feeds the entire planet. At first, the damage would be ecological. Plants depend on carbon dioxide. Over long timescales, as temperature and rainfall patterns change, the carbon cycle may draw carbon dioxide out of the atmosphere in ways that become difficult for plant life. Chemical weathering of rocks can remove carbon dioxide, and if that process outpaces volcanic replenishment, the atmosphere may become poorer in the gas plants need. The details are complex, but the broad danger is clear. A brighter sun does not merely make Earth warmer. It can disrupt the systems that keep the air, oceans, and biosphere stable. Forests would not simply catch fire everywhere at once. They would decline as conditions shifted beyond their tolerance. Some regions would become too hot, others too dry. Some ecosystems would migrate if they could, others would collapse. Animals would follow plants, water, and temperature zones until there was nowhere left that offered the right combination of food and climate. The planet would still be Earth. It would still have blue oceans for a while. It would still have clouds, storms, and coastlines. But the world that supported complex life would begin to narrow. This part of the sun's death is easy to overlook because it lacks spectacle. A red giant swallowing planets is dramatic. Oceans slowly becoming unstable over hundreds of millions of years is quieter. But for life, the quiet phase is the more important one. The biosphere does not need the sun to physically touch Earth to be destroyed. It only needs the sun to become bright enough that Earth can no longer regulate itself. Eventually, the oceans become the central problem. The The surface warms, evaporation increases, the atmosphere becomes wetter. High in the atmosphere, ultraviolet light from the sun can break water vapor apart into hydrogen and oxygen. Hydrogen is light. It can escape into space. This means that water, once lifted high enough and broken apart, can be slowly lost from the planet. Earth would not drain like a bathtub. The oceans would not vanish in one afternoon. But over geological time, the process could remove enormous amounts of water. This is one of the most haunting ideas in planetary science. A planet can lose its oceans upward, not through a crack in the seafloor, not by being knocked away by an asteroid, but by sunlight lifting water into the atmosphere, breaking it into pieces, and allowing part of it to leak into space. When we think of oceans, we imagine something permanent. They feel too large to disappear. But compared with a star, even an ocean is fragile. Earth contains a thin film of water wrapped around a ball of rock. From space, that film makes the planet look alive. In the future, the sun may slowly erase it. As Earth loses water, the surface changes. Coastlines retreat. Shallow seas dry out. Weather becomes harsher. Deserts spread. The familiar blue planet becomes less blue. Life, if it still exists, would retreat toward refuges, high latitudes, deep water, caves, underground aquifers. Perhaps microbial life could survive long after complex life disappears. Microbes have endured extremes on Earth that would kill most organisms immediately. They live in boiling springs, deep rock, frozen soils, acidic pools, and ocean vents, without sunlight. If anything remains when the surface becomes hostile, it may be microscopic. But even microbes have limits. As the sun grows brighter, the planet crosses thresholds. The surface becomes less forgiving. The oceans become smaller, then hotter, then increasingly unstable. Eventually, Earth may enter a moist greenhouse or runaway greenhouse state, depending on the exact conditions. A moist greenhouse would allow large amounts of water vapor into the upper atmosphere, where water loss accelerates. A runaway greenhouse would be worse. The planet would absorb so much heat that the oceans could not remain liquid in the long term. Venus may be an example of what happens when a rocky planet becomes trapped under a crushing greenhouse atmosphere, though Earth's exact path would not be identical. The important point is this: Earth becomes uninhabitable long before the sun reaches its final stages. This means that when people ask what happens when the sun finally dies, the answer begins with a disturbing correction. We are not waiting for the final death of the sun to threaten Earth. The slow aging of the sun is enough. The star that made life possible also sets a deadline for it. The same light that feeds plants and warms oceans is part of a long process that will one day push the planet past its limits. And still, at this point, the sun will not look dead. It will still be a yellow-white star in the sky. It will still be powered by hydrogen fusion. If there are observers somewhere in the solar system, they may not describe the sun as dying, but the future is already being written in its core. The balance is shifting. The hydrogen supply at the center is shrinking. The helium ash is building up. Gravity is waiting. When the core hydrogen finally runs low enough, the sun will enter a new phase. This is where the story changes from slow environmental decline to stellar transformation. For billions of years, the sun's core has been the main engine. Hydrogen fusion in the center has provided the energy that keeps gravity from compressing everything inward. But once the central hydrogen is mostly exhausted, the core can no longer produce enough energy in the same way. It is not that the entire sun runs out of hydrogen at once. There is still hydrogen in the outer layers. The problem is that the core, the place hot and dense enough for steady fusion, has changed. The helium-rich core begins to contract. Gravity presses it inward. As it contracts, it heats up. Around the core, a shell of hydrogen becomes hot enough to fuse. Instead of fusion occurring mainly in the center, hydrogen fusion begins in a shell surrounding the inert helium core. This shell burning releases energy into the layers above it. The outer parts of the sun respond by expanding. This is the beginning of the sun's transformation into a giant. At first, the change is not yet the enormous red giant people imagine. The sun enters a subgiant phase. It becomes larger and brighter. Its surface cools somewhat because the outer layers spread out over a greater area. A cooler surface changes the color of the star toward warmer shades, even as the total energy output increases. The sun begins leaving the calm main sequence behind. For Earth, this stage would be catastrophic if anything recognizable remained on the surface. The increased brightness would intensify the heating. Any remaining oceans would face impossible conditions. The atmosphere would change profoundly. Rocks would bake. The water cycle, if it still existed in some damaged form, would collapse. The planet might resemble a dead, overheated world, with a thick atmosphere and a surface stripped of the conditions that once allowed biology to flourish. The moon would still orbit Earth, but the view from its surface would be different. The sun would appear brighter, harsher, and gradually larger. The inner solar system would become a place of rising heat. Mercury, already scorched today, would be doomed. It orbits closest to the sun, and as the star expands, Mercury lies directly in the path of the growing outer layers. Venus would also face destruction. Venus is already a warning about what heat and atmosphere can do. Its surface today is hot enough to melt lead, hidden beneath clouds of sulfuric acid, and an atmosphere mostly made of carbon dioxide. But the dying sun would make even Venus's current hellish state temporary. Eventually, Venus would be engulfed or vaporized as the sun expands outward. Earth's fate is more uncertain in a technical sense, but not in a comforting one. The sun will lose mass as it evolves. As a star loses mass, the gravitational grip on planets weakens. Planetary orbits can expand outward. Earth may move slightly farther away as the sun sheds material. This raises a question scientists still examine. Will the expanding sun physically engulf Earth? Or will Earth's orbit move outward enough to avoid being swallowed? The answer depends on details of mass loss, tidal interactions, drag inside the sun's outer atmosphere, and the precise size the red giant sun reaches. But even if Earth avoids being swallowed, it does not survive as a living world. By then, the surface would be sterilized, the oceans would be gone, the atmosphere would likely be transformed or stripped. The crust would be heated to extreme temperatures. Earth might become a charred rocky remnant orbiting a bloated red star, or it might spiral inward and be consumed. Either way, the planet that once held forests, oceans, and cities would be gone in every meaningful sense. This uncertainty is almost more disturbing than a simple answer. If Earth is swallowed, it disappears into the outer layers of the sun, dragged through hot plasma until it breaks apart. If Earth is not swallowed, it remains as a burned corpse of a planet, lit by a swollen star that has destroyed everything that made it home. There is no version in which the Earth we know continues untouched. But to see why the sun becomes so large, we need to look deeper into the star. A red giant is not simply a star that has inflated like a balloon for no reason. It is the visible result of a changed internal structure. The core is no longer doing what it used to do. The helium core contracts and heats. The hydrogen-burning shell around it becomes extremely active. Energy flows outward. The outer layers expand because the star's internal pressure structure changes. As the star expands, its surface becomes cooler and redder, but the total luminosity can grow enormously because the surface area becomes so large. This is why a red giant can look cooler at the surface, but be more dangerous to nearby planets. Temperature and total power are not the same thing. A small, hot object can emit less total energy than a huge, cooler object. When the sun becomes a red giant, its outer surface will be cooler than the sun's current surface. but the star will be vastly larger and far more luminous. Earth would not be saved by the cooler color. It would be overwhelmed by the increase in total energy. The sky, if anything could stand beneath it, would become unrecognizable. The sun would no longer be a small, bright disk. It would swell until it occupied a much larger part of the sky. Shadows would change. Daylight would be redder and more diffuse. The idea of a normal sunrise would disappear as the star expanded and brightened. The old rhythm of Earth, sunrise, noon, sunset, night, would lose its meaning on a planet already ruined by heat. Before the red giant phase reaches its most extreme state, the sun will spend a long time changing. Stellar evolution is not a single step. It is a sequence. The sun leaves the main sequence. It becomes a subgiant. It climbs the red giant branch. The helium core grows hotter and denser. Hydrogen shell burning deposits more helium onto the core. This passage of everything goes on. It settles up to the peace. Again, there are access to the battlefield. In no way it seems that it's peculiar to the spectra of the fact that it's peace. You're not a false stranger, and it's emotion for the strangest, and nobody becomes experiences. It's raising, the outer layers swell. The star loses mass through a stronger stellar wind. Material flows away into space. The solar system is no longer sitting inside the steady environment it knows today. It is being filled with the breath of a dying star. That phrase sounds poetic, but it is physically real. The sun already emits a solar wind, a stream of charged particles that flows outward through the solar system. During its later giant phases, the sun will lose mass much more dramatically. Its outer layers will become less tightly held. Pulsations, radiation pressure, and stellar winds will push material away. The space between planets will no longer be the same thin environment shaped by the modern solar wind. It will contain more material from the aging sun. Dust and gas from the star itself will move outward, changing the conditions throughout the inner solar system. The planets will not be active participants in this story. They will be victims of orbital mechanics and radiation. Mercury is too close. Venus is too close. Earth is either too close or nearly too close. Mars, farther out, may avoid engulfment, but it will not be unchanged. A red giant sun would brighten Mars dramatically. The frozen carbon dioxide and water ice on Mars could respond to the increased warmth. For a limited time, parts of Mars might become less cold than they are today. The idea sounds hopeful until you remember the larger context. This would not be a stable second Earth. It would be a brief warming under a dying star, in a system being transformed by mass loss and radiation. Farther out, the story becomes stranger. The habitable zone, the region where temperatures might allow liquid water under the right conditions, would move outward as the sun brightens. Places too cold today could temporarily receive more warmth. The icy moons of Jupiter and Saturn might experience changes. Europa, Ganymede, Callisto, Titan, and other frozen worlds could be warmed by a more luminous sun. Ice may soften or sublimate. Atmospheres may thicken briefly. Chemistry may change. Some scientists have wondered whether outer solar system worlds could become more temperate for a limited period during the sun's red giant future. But this is not a comforting rescue plan. The red giant phase is unstable and temporary compared with the main sequence. The environment would be changing rapidly on astronomical timescales. The star would be losing mass. Radiation conditions would shift. Orbits would adjust. The outer worlds might experience a strange late spring, but it would not last like Earth's long habitable era. It would be a brief window near the end of the solar system's familiar history. This is one of the most eerie parts of the sun's death. Habitability does not simply vanish from one place, it moves. The zone of warmth migrates outward as the star evolves. Earth loses its place. Mars may warm, icy moons may thaw in some regions, but the movement is not gentle or permanent. It is like a campfire growing out of control. The place that was comfortable becomes burned. The cold ground farther away becomes warm for a while. Then, the fire changes again. At the center of all of this is a core that keeps contracting. The helium core becomes hotter as gravity compresses it. But helium fusion requires much higher temperatures than hydrogen fusion. Hydrogen can fuse in the sun's core today because the conditions are extreme enough. Helium nuclei with greater charge repel each other more strongly. To fuse helium into heavier elements, such as carbon and oxygen, the core must become much hotter. For a long time, the core is not hot enough. It contracts. It heats. The hydrogen shell keeps burning. The outer layers keep expanding. The sun becomes more luminous. The red giant grows. The inner planets face their end. To make the timeline feel real, it helps to separate two different kinds of danger. The first danger is biological. This is the danger to life, water, ecosystems, and climate. It begins while the sun still looks like the same star. It is the danger of receiving just a little too much light for too long. The second danger is physical. This is the danger to the planet as an object. It comes later, when the sun expands, when its outer atmosphere reaches across the inner solar system, and when Earth is either dragged into the swollen star or baked into a lifeless remnant. Those two dangers do not arrive together. This matters because many people imagine the future as if Earth remains completely fine until the sun becomes a giant. In reality, the biological deadline comes first. The world becomes harder for life long before it becomes physically threatened by the star's surface. If a future civilization wanted to survive, it would not have to wait for the red giant phase to realize there was a problem. It would notice the steady rise in solar brightness, the movement of the habitable zone, the growing instability of the climate, and the slow closing of Earth's natural window for life. That phrase, habitable zone, can sound too simple. It is often described as the region around a star where liquid water can exist on a planet's surface. But the real idea is more delicate. A planet can sit inside the habitable zone and still be dead. It can have the wrong atmosphere, the wrong mass, the wrong rotation, the wrong magnetic protection, or no water at all. A planet can sit outside the traditional habitable zone and still hide liquid water beneath ice if internal heating is strong enough. Habitability is not just distance. It is a balance between a star, a planet, an atmosphere, geology, chemistry, and time. Earth has enjoyed that balance for an extraordinary period. Liquid water has existed on the surface for billions of years. Life has had enough time not only to appear, but to transform the atmosphere, build complex ecosystems, survive disasters, and eventually produce intelligence. That long stability is not guaranteed for rocky worlds. Some planets are too close to their stars and become overheated early. Some are too far away and freeze. Some lose their atmospheres. Some never develop the right chemistry. Some orbit stars that flare violently. Some are struck too often by large impacts. Earth has not been perfectly safe, but it has been safe enough for a very long time. The aging sun is the final limit on that long safety. The sun's brightness is not rising because it is angry or unstable. It is rising because the internal core conditions change as hydrogen turns into helium. The core adjusts. The outer layers respond. The luminosity slowly increases. This is built into stellar evolution. Every main sequence star changes over time. Some change quickly because they are massive and burn fuel rapidly. Some change slowly because they are small and efficient. The sun sits between those extremes. It lives long enough for life to evolve, but not forever. This is why the sun is both generous and temporary. A more massive star might provide more light, but it would die much sooner. A smaller red dwarf might live for trillions of years. But its planets can face other problems, such as tidal locking and powerful flares, especially early in the star's life. The Sun gave Earth a long, steady chapter. That chapter is not endless. Its length is part of what made us possible, and its ending is part of what makes the future unavoidable. Now imagine a scientist far in the future, not a human scientist necessarily, but any intelligent observer with instruments watching the Sun across millions of years. They would not see chaos at first. They would see trends. Solar luminosity would creep upward. The spectral output would remain broadly familiar, but the total energy would slowly increase. Earth's climate models would need constant updating. The old assumptions would fail. Agriculture, if it still existed on the surface, would have to move. Cities, if they existed, would adapt with engineering. Reflective shields, orbital mirrors, underground habitats, and controlled biospheres might extend survival for a time. But these would be temporary strategies against a star whose direction cannot be reversed. A civilization with enough technology might leave Earth. That possibility changes the emotional shape of the story, but not the physical one. If our descendants, or some other form of intelligence, survive long enough, they may migrate outward. They may build habitats in space, move to moons, mine asteroids, or create artificial worlds that can control their own climates. They may no longer depend on the surface of Earth. In that case, the death of Earth would not necessarily be the death of life from Earth, but it would still be the death of the birthplace. There is a difference between surviving and staying home. Earth is not just a location with the right temperature. It is the place where life emerged, where oceans shaped chemistry, where continents drifted, where the atmosphere filled with oxygen, where everything we know began. Even if intelligence someday escapes the planet, the loss of Earth would still be the end of the original garden. The Sun's aging turns our home into a temporary shelter. This is what makes the topic so powerful for a quiet night. The danger is not a monster from outside the solar system. It is not a rogue black hole, a gamma ray burst, or an alien weapon. It is the normal future of the star we depend on. The most familiar object in the sky contains the ending of the world inside it. The Sun today is stable because of equilibrium. Gravity pulls inward. Pressure pushes outward. Energy flows from the core through the radiative zone, then through the convective outer layers, and finally escapes from the visible surface called the photosphere. That escaping energy travels through space and reaches Earth about 8 minutes later. We feel it as warmth. Plants use it as fuel. Weather systems are driven by it. Solar panels catch it. Our entire surface environment is tuned around it. Inside the Sun, energy does not travel simply. Photons produced in the core do not fly straight out. The core and inner layers are dense, and photons scatter many times. A packet of energy can take an extremely long time to work its way outward, being absorbed and re-emitted again and again. By the time energy reaches the surface and escapes as sunlight, it has been processed through the structure of the star. The Sun's calm face hides a complicated interior. That interior is slowly becoming less like the Sun of the past and more like the Sun of the future. The core's composition changes. Helium accumulates. The region of active hydrogen fusion evolves. The star adjusts to maintain balance, but every adjustment points toward the same destination. Eventually, the current arrangement cannot continue. The Sun is not failing because something unusual happens to it. It is failing because everything is proceeding normally. This is a strange kind of horror. Most terrifying events feel wrong. A star's death feels natural. It is exactly what should happen. The universe is not breaking its rules. It is following them perfectly. Long before the red giant phase, the Moon would become a witness to Earth's transformation. The Moon itself has no oceans, no air, and no biosphere to lose. It is already a dry, silent world. But from the moon's surface, future Earth would change dramatically. The blue color would fade as oceans shrink. White cloud patterns would change as the atmosphere becomes hotter and wetter, then eventually drier in some layers as water is lost. The night side of Earth might glow differently as the surface heats. If oceans vanish completely, Earth would no longer reflect light in the same way. The moon would still be tidally locked, still showing the same face to Earth, but the world hanging above its horizon would no longer be the living planet we recognize. The moon's orbit would also continue to evolve. Today, the moon is slowly receding from Earth, moving away by a few centimeters each year. Over billions of years, that adds up. Earth's rotation slows as tidal interactions transfer angular momentum to the moon's orbit. Days become longer. The future Earth-Moon system would not have the same rhythm it has today. By the time the sun reaches later stages, Earth may rotate more slowly, the moon may be farther away, and the familiar cycles of tides and days would be altered. These changes are small compared with the sun's transformation, but they remind us that nothing in the solar system is frozen. Even the planets are not fixed props. Their orbits are stable over human timescales, but over billions of years, gravitational interactions, solar mass loss, and tidal effects can change the architecture of the system. As the sun loses mass during its giant phases, the gravitational pull on the planets weakens. Orbits can expand. The outer planets drift into slightly wider paths. The solar system loosens. It does not explode outward. The change is more subtle, but the old arrangement becomes stretched. This mass loss is part of the reason Earth's physical fate is uncertain. If the sun kept all its mass while expanding, the outcome would be simpler, but the sun will shed material. Earth may move outward. At the same time, if Earth enters the outer layers of the giant sun, drag and tidal forces could pull it inward. The balance between outward orbital expansion and inward decay is complicated. Some models suggest Earth may be engulfed. Others allow a possibility that Earth avoids direct engulfment while still being completely sterilized. For storytelling, the uncertainty does not weaken the ending. It makes it more realistic. Science is not always a single dramatic sentence. Sometimes the honest answer is, we know the Earth will not remain habitable, but the exact physical final state is still uncertain. That uncertainty is not comforting, because every likely version is devastating. Engulfed Earth and roasted Earth are not meaningfully different from the perspective of life. Both are endings. As the sun swells, Mercury becomes the first clear sacrifice. Mercury is a small, rocky world with almost no atmosphere. It has spent its existence under intense sunlight, with days hot enough to melt some metals and nights cold enough to freeze gases. Its surface is ancient and cratered, a record of impacts and solar exposure. But during the sun's red giant expansion, Mercury's orbit lies too close. The planet would face heating beyond anything it experiences now. Rock would melt. Surface materials would vaporize. Eventually, Mercury would be destroyed or swallowed by the expanding star. Venus comes next in the line of danger. Venus already shows us that being similar in size to Earth is not enough. It is almost Earth's twin in diameter and mass, but its atmosphere turned it into a furnace. Thick carbon dioxide traps heat. Sulfuric acid clouds reflect sunlight, but also hide a crushing environment below. The surface pressure is about 90 times Earth's, and the temperature is hotter than Mercury's average surface temperature, despite Venus being farther from the sun. During the sun's dying expansion, Venus would not remain a stable planet. It would be overwhelmed by the growing star. Earth follows as the emotional center of the story, not because it is physically the largest or most important planet, but because it is ours. A distant observer might classify Earth as one inner rocky planet among several. A scientific diagram might show it as a dot, at 1 astronomical unit from the Sun. But for life, Earth is not just a dot. It is the only known world with forests, oceans, animals, technology, memory, and observers capable of understanding stellar death. The Sun's future is not only an astrophysical sequence, it is the future of the only living world we know. The first visible signs of Earth's final decline would probably not be cinematic. They would be statistical. Average temperatures rising over deep time, weathering rates changing, carbon dioxide levels shifting, biodiversity patterns narrowing, ocean chemistry altering, the biosphere losing flexibility. Life can adapt to many changes, but adaptation requires time, diversity, and available niches. A brightening sun compresses possibilities. It does not chase life with flames at first. It removes options. Eventually, the tropics could become unlivable for complex organisms. Heat stress would make survival difficult. Wet bulb temperatures, which combine heat and humidity, could cross thresholds where animals cannot cool themselves. Regions that once supported lush ecosystems might become lethal. Life would retreat toward cooler places, perhaps higher latitudes or higher elevations. But as the energy imbalance grows, even refuges would fail. In the oceans, warming would alter circulation, oxygen levels, and chemistry. Marine life depends on temperature ranges and dissolved oxygen. Warmer water holds less oxygen. Stratified oceans mix differently. Acid-base chemistry changes. Reef systems would be gone long before the final extreme stages. Plankton communities would shift. Food webs would reorganize or collapse. The ocean, which seems like the most stable environment on Earth, would not be immune to a brighter sun. The end of habitability would not be a single extinction event. It would be a sequence of losses. Large animals first, complex ecosystems, plants in many regions, marine food chains, then more resilient organisms. Microbes could continue in protected environments, but even their world would shrink. The deep subsurface might remain habitable longer than the surface, warmed by Earth's internal heat and shielded from the worst sunlight. Life beneath the crust might persist in cracks and pores where liquid water remains, if water remains. But the surface biosphere would be gone. From space, future Earth might still look like a planet for a long time after it stops being alive. This is important. Habitability and appearance are not the same. A world can look beautiful and be deadly. Venus is bright and stunning in the sky, yet its surface is a nightmare. Future Earth might retain clouds, colors, and atmospheric patterns while being hostile to life. Later, as water disappears, it would become visibly different. But there may be a long period when the planet still looks like a world, even as its living systems fail. That is one reason exoplanet science is so difficult. When astronomers study distant planets, they often get tiny clues: a dip in starlight, a mass estimate, a radius, maybe hints of atmospheric composition. A planet can sit in a promising orbit and still be dead. A planet can look Earth-sized and still be Venus-like. A planet can have clouds and still be hostile. The future of Earth reminds us that habitability is time-dependent. A planet may be habitable for a chapter, then lose that status as its star evolves. Earth's chapter has been long, but it is not permanent. The same will be true for countless other worlds around other stars. Every planet's future is tied to stellar evolution. Around some stars, habitable eras are brief. Around others, they may last much longer than Earth's. But no ordinary star remains unchanged forever. The search for life is also a search for timing. You need a planet in the right place, with the right conditions, during the right part of its star's life. Our timing, so far, has been extraordinary. We exist during the sun's stable middle age, after Earth has had billions of years to develop complexity, but before the star's aging has pushed the planet out of habitability. We can study the sun while it still supports us. We can understand its future before that future arrives. This is a rare kind of knowledge. Most species that have lived on Earth had no idea what the sun was. They lived under it, depended on it, and died without knowing that their star had a life cycle. Humans are different only because we can measure. We can split sunlight into spectra and learn its composition. We can model nuclear fusion. We can observe other stars at different stages of life and use them as examples of what our sun will become. We can see red giants, planetary nebulae, and white dwarfs scattered across the galaxy. The sun's future is not guessed from imagination alone. It is reconstructed by studying stellar populations, physics, and the life cycles of stars. Every red giant in the night sky is a preview. Some of those stars may once have had planets. Some may have warmed worlds for billions of years. Some may have destroyed inner planets during their expansion. When we look at them, we are not just seeing distant objects. We are seeing stages of a process our own star will eventually follow. The galaxy is full of reminders that the sun is not unique in this way. One day, to a distant alien astronomer, our sun may look like one of those examples. They might observe it as a swollen red giant. They might detect dust from its mass loss. They might infer that inner planets were lost or transformed. They might never know that one of those planets once had oceans, continents, life, and a species that predicted the whole thing billions of years in advance. That thought gives the story a different kind of weight. The death of the sun is not only about the future, it is about the fact that the present is temporary. The calm star above us is in the middle of a path. We are living inside one particular moment of that path, and everything familiar depends on that moment lasting. As the red giant phase approaches, the sun's outer atmosphere becomes enormous and thin. This can be confusing. When people hear that the sun may expand to reach near Earth's orbit, they imagine a solid surface moving outward, like a wall. But a red giant's outer layers are extremely diffuse compared with the sun's current interior. The star becomes huge, but its outer atmosphere is spread over a vast volume. If Earth were inside those outer layers, it would not be like hitting a solid object. It would be moving through hot, thin plasma. But that plasma would still create drag, heat, and destructive interactions over time. A planet orbiting inside a star's extended atmosphere cannot remain normal. Drag removes orbital energy. The planet spirals inward. It heats. Its surface is stripped and melted. Material can be pulled away. Eventually, it can disintegrate or merge with the star. The process may not look like a single explosion. It may be a drawn-out destruction, with the planet losing its identity as it moves through the outer layers of its dying parent star. If Earth avoids that fate, the alternative is bleak. A scorched Earth outside the red giant's reach would still endure extreme radiation and heat. Its surface could melt in places. Its atmosphere may be removed or transformed. The crust might become unrecognizable. The moon, if still bound, would orbit a dead world. The pair would continue circling the aging sun, but the meaning of Earth as a living planet would already be ancient history. By this point, the sun itself would look majestic from a safe distance. This is one of the strange contradictions of astronomy. A red giant can be beautiful. It can glow with a deep orange or red light. It can be vast and luminous, surrounded by material flowing into space. Through a telescope, dying stars can look delicate, colorful, and almost peaceful. But that beauty is not gentle for planets nearby. The same process that creates a stunning cosmic object can erase the worlds that once orbited close to it. The universe often works this way. Nebulae can be beautiful because stars die. Heavy elements can exist because earlier stars lived and exploded or shed their layers. Planetary systems can form from the remains of older generations. Cosmic beauty is not separate from destruction. It is often produced by it. Our sun's death will eventually contribute material back into space, not in the first half of the process, but later, as it loses its outer layers. Those layers contain material that once helped make up the sun's envelope. Some of that material has been altered by nuclear processes and mixing. It will spread outward, enriching the space around the dying star. The sun will not explode as a supernova because it is not massive enough. Its ending is gentler than the death of a massive star, but gentle is a relative word. For Earth, it is still total. This distinction is important for accuracy. The sun will not go supernova. It does not have enough mass. Massive stars die by core collapse, creating supernova explosions, neutron stars, or black holes. The sun's fate is different. It will become a red giant, shed its outer layers, and leave behind a white dwarf. That means the solar system is not destined for a sudden blast that destroys everything instantly. Its fate is slower, more graceful from afar, and more haunting because it gives time for each stage to unfold. A supernova is a scream. The sun's death is a long exhale. In part 1, we are still before that final exhale. We are watching the star age, brighten, destabilize Earth, and expand toward the red giant stage. The final shedding of the outer layers belongs to the later chapter, but the groundwork is already here. The core is changing. The outer layers are responding. The planets are losing the stable environment that defined their history. The modern solar system is a snapshot, not a permanent design. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, the Kuiper Belt, and the distant icy bodies beyond are all arranged around the sun as it exists now. But as the sun evolves, the energy landscape changes. Orbits may widen as mass is lost. Temperatures change. Volatile ices sublimate in places where they were once stable. Dust dynamics shift. Radiation pressure changes. The heliosphere itself, the bubble carved by the solar wind, would not behave as it does today. The sun's dying phases would reshape not only planets, but the space between them. Today, the heliosphere surrounds the solar system like a protective bubble, formed by the solar wind pushing against the interstellar medium. During later stages, the character of the solar wind changes. The sun's mass loss becomes stronger. The bubble around the solar system could expand or alter, depending on the wind and the surrounding interstellar environment. The solar system would be embedded in the aging atmosphere and wind of its star. For any spacecraft still operating in that distant future, the environment would be unfamiliar. Of course, our current spacecraft will be long dead by then. Voyager, Pioneer, New Horizons, and other probes will be silent relics in interstellar space or on distant trajectories. But imagining instruments watching the sun's future helps us understand the physical changes. They would record rising luminosity, changing particle flows, stronger mass loss, altered radiation, and the expansion of the star's outer layers. The sun would become a variable, evolving presence rather than the steady anchor we know. This is why the question, what happens when the sun finally dies, cannot be answered with only the final object. Yes, the sun becomes a white dwarf eventually, but that is the end state. The story is the path. The path includes the destruction of habitability, the transformation of the inner planets, the swelling of the star, the movement of the habitable zone, the loss of solar mass, and the strange possibility that frozen worlds far away may briefly warm under a dying sun. The path is what makes the ending terrifying. If we skip straight to the white dwarf, we miss the long collapse of everything familiar. We miss the fact that the sun's death begins while it still shines. We miss the slow erasure of oceans. We miss the red giant sky. We miss the uncertainty of Earth's final physical fate. We miss the way a stable solar system becomes an aging system. And perhaps most importantly, we miss the timescale. 5 billion years is so long that the number almost loses meaning, but it is not infinite. The universe is old enough for such spans to matter. Earth itself is about 4.5 billion years old. Life has existed for much of that time. Another few billion years is comparable to the entire history of our planet so far. The future before the sun's final stages is vast, but it is not empty. It is enough time for continents to rearrange, species to evolve, civilizations to rise or vanish, and perhaps intelligence to leave the planet entirely. The sun's death is far away, but it is not imaginary. It is a real future event predicted by the same physics that explains why the sun shines today. The fact that it is distant does not make it fiction. It makes it cosmic. When we watch the sun set, we are seeing a star in the middle of its life. It drops below the horizon because Earth turns, not because the sun changes. Tomorrow, it returns. That daily reliability shapes our minds. We associate the sun with renewal, morning, warmth, growth, time. But beneath that daily rhythm is a much larger rhythm. The sun itself has a morning, a long noon, an old age, and an ending. We are living in the long noon. For now, the sun is stable enough that human beings can worry about immediate problems instead of stellar evolution. The oceans are still here. The atmosphere still protects us. Plants still use sunlight. The moon still reflects it. The planets still move through a solar system that would be recognizable to ancient astronomers if they could see it through modern telescopes. But the laws that protect this moment are the same laws that will end it. Fusion gives the sun light. Fusion consumes fuel. Gravity holds the star together. Gravity will compress the core when the fuel changes. Radiation warms Earth. Radiation will one day overheat it. The same mechanisms that made habitability possible contain the mechanism of its end. This is not a contradiction. It is the nature of stars. The sun is not a lamp placed in the sky for Earth. It is a physical object following its own evolution. Earth benefits from that evolution during one chapter. When the chapter changes, Earth does not get to choose a different star. That realization can feel cold, but it also makes the present more remarkable. For billions of years, conditions aligned. The sun's output, Earth's orbit, the atmosphere, the carbon cycle, oceans, plate tectonics, the magnetic field, and life's own feedbacks created a world where complexity could emerge. None of it was guaranteed. None of it is permanent. The future red giant sun does not make the present meaningless. It makes the present rare. And now, as we approach the end of the first half of this story, the sun is no longer the familiar star of our daily sky. In the timeline we are following, it has brightened beyond Earth's comfort. It has pushed life toward extinction. It has begun to leave the main sequence. Its core has changed from a hydrogen-burning engine into a contracting helium center, surrounded by a burning shell. Its outer layers are expanding. Mercury and Venus face destruction. Earth stands at the edge of either engulfment or survival, as a dead rock. Mars and the outer worlds wait under a changing light. The sun is becoming a red giant, but a red giant is not the final answer. Inside the swollen star, the core continues to heat. The pressure rises, the helium waits for conditions extreme enough to ignite. When that happens, the sun enters another stage, one that will decide how it sheds its outer layers and what kind of remnant it leaves behind. That is where the next part of the story will go, because the sun's final death is not the moment it becomes huge. It is the moment after the giant phase when the star loses its outer body, exposes its core, and leaves the solar system orbiting a fading white ember. That remnant begins with a change deep inside the swollen star. By the time the sun has become a red giant, it will no longer be the simple hydrogen-burning star we know today. The core, once the steady furnace of the solar system, will be packed with helium ash left behind by billions of years of fusion. Hydrogen will still burn, but not in the central core. It will burn in a shell around that helium center, adding more weight, more pressure, and more heat to the star's interior. From the outside, the sun may look almost like a cosmic disaster unfolding in slow motion. Its surface will be huge, cooler, redder, and far more spread out than it is now. But the surface is not where the most important part of the story is happening. The real turning point is hidden inside a core no telescope could see directly. A core squeezed so tightly that matter begins to behave in ways that feel completely unlike ordinary gas. Here, gravity has not stopped working. It never stops. When fusion cannot push back in the center, gravity keeps compressing the helium core inward. Compression raises the temperature. The hotter core presses harder against itself. But in a red giant, the core can become supported by electron degeneracy pressure, a quantum mechanical effect that does not depend on heat in the same normal way that gas pressure does. That sounds abstract, but it matters because it changes the way the star responds to rising temperature. In ordinary gas, if the core heats up, it expands, and expansion cools it. That creates a natural safety valve. But in a degenerate core, the pressure is not controlled mainly by temperature. The material can grow hotter without expanding enough to relieve the situation. So the helium waits. It is not waiting consciously, of course. It is not storing anger or planning an explosion. But physically, it is being pushed toward a threshold. The nuclei inside the core are moving faster and faster. Eventually, the temperature becomes high enough for helium nuclei to fuse together. Hydrogen fusion built the sun's long main sequence life. Helium fusion will define its strange old age. When helium fusion begins in a star like the sun, it can start suddenly in what astronomers call the helium flash. The name sounds dramatic, and in one sense it is. In the core, an enormous amount of energy is released as helium nuclei combine to form carbon and oxygen. But this is not a supernova. It does not blast the sun apart. It does not send a visible flash across the galaxy. The energy is trapped, absorbed, and used to lift the core out of its degenerate state. From the outside, the helium flash would not look like a sudden cosmic firework. The swollen sun would adjust. Its internal structure would reorganize. Its outer layers would shrink somewhat, compared with the largest red giant stage, and the star would settle into a new phase of life. This is one of the strange lessons of stellar death. Some of the most violent changes happen invisibly. A star can transform its core while the surface changes only gradually. To anyone watching from far away, the sun would remain a red giant, but inside, it would have crossed an irreversible line. For a while, the sun would burn helium in its core. This stage would not last nearly as long as the hydrogen burning life it has now. Hydrogen fusion has kept the sun shining for billions of years because hydrogen is abundant and the process is relatively slow. Helium burning is more demanding. It requires higher temperatures and the fuel supply is smaller. The sun would spend only a fraction of its life in this phase, using helium to make carbon and oxygen in the center. At this point, the solar system would already be unrecognizable. Mercury would almost certainly be gone. Venus would likely be destroyed. Earth, if not swallowed outright, would be a scorched remnant orbiting close to a star that had already erased everything living from its surface long before. The moon would still be nearby if Earth survived, but it would no longer light oceans or clouds. It would circle a dead rock under a red and swollen sky. Mars might become warmer for a time, not comfortable in the way Earth is comfortable now, but less frozen than before. The outer solar system would experience its own temporary transformation. Moons that once locked their water beneath thick ice might thaw at their surfaces. Icy bodies in the asteroid belt, Kuiper belt, and beyond could begin to release vapor as the dying sun grows brighter. The habitable zone, that moving band of distances where liquid water could exist under the right conditions, would shift outward. This does not mean the outer solar system becomes paradise. It means the place of warmth moves. Worlds that spent billions of years in darkness might briefly receive enough sunlight to change. Frozen surfaces could crack, ancient ices could vaporize. Comets might become active at distances where they once remained silent. The death of the sun would not happen as a single clean event. It would be more like the solar system being rewritten in chapters. Inner planets burn, outer worlds thaw, orbits shift as the sun loses mass. Dust, gas, ice, and rock respond to a star that is no longer stable in the way it used to be. During the helium burning stage, the sun would still have a core energy source. It would still be alive in the stellar sense. But even this second life would have an ending. Once the helium in the core is mostly used up, the center will be left with carbon and oxygen. For a more massive star, that might become the beginning of another chain. Carbon could ignite, then neon, oxygen, and silicon could follow until the star builds iron in the core and sets the stage for a supernova. But the sun is not massive enough for that. This is one of the most important facts about our star's death. The sun will not explode as a supernova. It will not collapse into a neutron star. It will not become a black hole. Those endings belong to stars born with much greater mass. The sun's fate is quieter, but not gentle. It will try to go further, but it cannot. The carbon-oxygen core will not reach the temperature required to ignite carbon fusion. Gravity will compress it, but the sun simply does not have enough mass to crush the core to the next stage. Instead, fusion will continue in shells around the dead center. Helium may burn in one shell, hydrogen may burn in another. The outer layers will swell again. The sun will enter the asymptotic giant branch, one of the most unstable and dramatic phases in the life of a sun-like star. If the first red giant phase was the beginning of the end, this stage is the star losing control of its own body. The outer layers grow enormous and loosely held. The core is compact and hot. Shells of fusion switch on and off in complicated rhythms. The star pulses, it brightens and dims, its surface expands and contracts. Powerful stellar winds begin to carry material away into space. The sun that once held its planets in stable light for billions of years will begin throwing itself outward. These winds will not look like ordinary wind. There is no air rushing across the surface in the way wind moves through Earth's atmosphere. Stellar wind is the flow of particles streaming away from the star. During the sun's current life, it already produces the solar wind, a thin stream of charged particles that fills the heliosphere. But near the end, the mass loss becomes far more intense. The dying sun will shed a large fraction of its outer envelope. Every second, material that once belonged to the star will drift into space. Hydrogen, helium, carbon, oxygen, and other elements will leave the sun and spread through the solar system. The star will become surrounded by its own escaping atmosphere. This is where the beauty and the horror of stellar death meet. A dying sun-like star does not simply go dark. It leaks itself into the surrounding void. Its outer layers float away, illuminated by the hot core that remains behind. The material expands, thins, and forms a glowing shell. Astronomers call this a planetary nebula, even though it has nothing to do with planets. The name came from early telescopes, where these round, fuzzy objects looked a little like planetary disks. In reality, a planetary nebula is a star's final exhalation. If some distant civilization existed far away and looked toward our solar system at the right time, they might see a glowing cloud where the sun once shone. It could appear as a delicate ring, a shell, a distorted bubble, or a more complex structure shaped by magnetic fields, rotation, and the last uneven breaths of the star. The sun's outer layers would become a temporary nebula, expanding into interstellar space. Temporary is the key word. A planetary nebula does not last forever. Compared with the star's long life, it is brief. The glowing gas may remain visible for only tens of thousands of years before it disperses and fades into the interstellar medium. After billions of years of steady sunlight, the final colorful display is almost a blink. But during that blink, the sun will reveal what it really was made of. The material escaping from the star will carry elements created inside it and elements inherited from earlier generations of stars. Hydrogen from the early universe, helium forged in the Big Bang and inside stars, carbon and oxygen made during the sun's old age, tiny traces of heavier elements that existed in the cloud from which the solar system formed. This is how stars recycle matter. A star like the sun cannot make iron in its core. It cannot produce the heaviest elements through its own fusion, but it can return lighter elements to space and enrich the material between stars. Over long cosmic times, that material can mix with other gas and dust. It can become part of new molecular clouds. Those clouds can collapse, new stars can form, new planets can grow around them. The atoms that once passed through the sun may one day become part of something else. Not the same sun, not the same Earth, not the same solar system. But matter is not sentimental. It moves through cosmic cycles without remembering its old shape. The calcium in a future rock, the carbon in a future atmosphere, or the oxygen in a future ocean could include particles that once moved through the outer layers of our dying star. Still, for anything left in the solar system, the planetary nebula phase would not feel poetic. It would be the aftermath of destruction. The sun's mass loss would change the orbits of surviving planets. Gravity depends on mass. As the sun sheds material, its grip weakens. Planets that remain outside the engulfment zone would drift into wider orbits. Mars, Jupiter, Saturn, Uranus, and Neptune would not suddenly fly away, but their paths would expand. The architecture of the solar system would loosen. This matters for smaller bodies even more. Asteroids, comets, Kuiper Belt objects, and distant icy bodies would be disturbed. Some would move onto new trajectories. Some might be thrown inward. Some could collide with planets or moons. Others could be ejected into interstellar space. The neat solar system we imagine today would become messy, rearranged by the death of its central star. And then, after the outer layers are gone, the core would finally stand exposed. That core is the white dwarf. A white dwarf is not a normal star. It is not fusing hydrogen. It is not generating energy in the way the sun generates energy today. It is the leftover heart of a star, compressed into a sphere roughly the size of Earth, but containing a large fraction of the sun's original mass. Imagine something with a mass comparable to the sun squeezed into a volume similar to our planet. The density becomes almost impossible to picture. A spoonful of white dwarf material would weigh tons on Earth. The object is supported again by electron degeneracy pressure, the quantum resistance of electrons being forced into the same states. The white dwarf is hot at birth, very hot. The exposed core can glow with temperatures far above the present surface temperature of the sun. It shines not because new fusion is powering it, but because it still contains trapped heat from its former life. It is a stellar ember, bright at first, then slowly cooling. This is the sun's true corpse. Not a black hole, not an explosion, not a dramatic disappearance. A compact, hot, fading remnant surrounded by whatever is left of its planetary system. At first, the white dwarf would emit intense ultraviolet radiation. That radiation would light up the surrounding gas and make the planetary nebula glow. The nebula would be the visible cloud. The white dwarf would be the central engine illuminating it. Over time, as the gas expands and thins, the nebula would fade. The white dwarf would remain. The solar system would then enter a new era. There would still be a central object, There would still be gravity. Some planets might still orbit. Jupiter and the outer giants would likely survive, though farther out than before. Their moons would still circle them. Rings, if they lasted, would still be sculpted by gravity. The Kuiper Belt might still contain icy remnants, though disturbed. The Oort cloud, if it remained bound, would be stretched and vulnerable to passing stars and galactic tides. But the old sunlight would be gone. The white dwarf would shine, but not like the sun. It would be smaller, dimmer, and gradually cooling. It could illuminate nearby debris, but it would not provide the broad warmth that once powered Earth's climate, oceans, weather, and biosphere. The solar system would not become completely dark at once, but it would become cold in a way that no planet could repair on its own. If Earth survived, it would orbit a dead star. There is something almost impossible to imagine about that. The same world where forests grew, oceans moved, storms formed, and civilizations looked upward could become a burnt rock circling a white dwarf. Continents would no longer matter as continents. Oceans would be gone. The atmosphere would likely be stripped, altered, or collapsed. The surface would preserve only traces of a story that nobody was left to read. And if Earth did not survive, if it was swallowed during the red giant phase, then the planet itself would become part of the sun's outer layers before those layers escaped into space. The atoms of Earth would mix into the dying star's envelope. Rock, metal, water, atmosphere, and everything built on the surface would be erased as a planet and returned to the star that once made life possible. Either ending is difficult to hold in the mind. Survival as a dead planet is not rescue. Engulfment is not simply burning. Both are ways of leaving the world we know behind. But the outer planets would continue. Jupiter may become the most important surviving body in the post-sun solar system. It is massive enough to shape the motion of smaller objects and stable enough to persist through the sun's transformation. Saturn, Uranus, and Neptune would also remain as cold giants around a fading remnant. Their moons, once bathed in weak sunlight, would enter deeper cold. For a time, during the red giant phase, some outer moons might have experienced increased warmth, but after the white dwarf forms, that warmth would vanish. Icy surfaces would freeze hard again. Any temporary atmospheres created by solar heating would collapse or escape. The chemistry of those worlds would slow. The solar system would not be destroyed in one sweep. It would become a graveyard with motion. Planets would still orbit. Moons would still keep time. Comets would still move along elongated paths. But without a living sun, the system would lose the energy source that gave it climate, weather, liquid water on Earth, and most of the dynamic surface activity that depends on sunlight. There might be exceptions. Worlds with internal heat could remain active. Jupiter's moon Europa, Saturn's Enceladus, and other icy moons are shaped not only by sunlight, but by tidal heating, radioactive decay, and internal processes. A white dwarf sun would not immediately remove every hidden ocean. Some subsurface environments might persist for a long time if their heat sources lasted, but the solar system as a whole would become colder, darker, and more isolated. This is why the death of the sun is not just about one star. It is about the collapse of an entire energy system. For Earth today, sunlight is so constant that we treat it as background. It wakes the atmosphere into motion. It powers evaporation, winds, storms, photosynthesis, and the food chains built on plants and algae. It sets the rhythm of days and seasons. Even fossil fuels are ancient sunlight stored in chemical bonds by life long ago. Solar energy reaches into almost every part of the world. When the sun dies, that relationship ends. The white dwarf may remain beautiful through a telescope, but beauty is not habitability. A glowing remnant is not a stable main sequence star. It is cooling, not sustaining. It is the memory of a furnace, not the furnace itself. In the first millions of years after becoming a white dwarf, the remnant would still be hot. It might even have a narrow region around it where a planet could, in theory, receive enough energy for liquid water. Scientists sometimes discuss habitable zones around white dwarfs. The idea is not fantasy. A small, close-in planet around a cooling white dwarf could have temperatures that allow liquid water for a time, but the conditions would be difficult. A planet would need to orbit very close to the white dwarf, much closer than Earth orbits the Sun today. It might become tidally locked, with one side always facing the remnant and the other side in darkness. It would need to have survived the red giant phase or formed again from leftover debris. It would need an atmosphere, water, and stability. It would also face a cooling star, so the habitable zone would slowly move inward as the white dwarf fades. Around a white dwarf, habitability is not impossible, but it is fragile. For our own solar system, Earth is unlikely to become a comfortable white dwarf planet. Its earlier destruction or sterilization makes that idea mostly, but the concept tells us something important. Even dead stars may still host worlds. Even after stellar death, orbital systems can continue. The universe does not divide cleanly into living and dead places. There are transitions, leftovers, temporary possibilities, and strange second chapters. Astronomers have found evidence that white dwarfs can be surrounded by debris. Some white dwarfs show heavy elements in their atmospheres, even though those elements should sink out of sight quickly in such dense objects. The likely explanation is that asteroids, comets, or planetary fragments fall onto the white dwarf, polluting its surface layers. In other words, many white dwarfs are still eating the remains of their planetary systems. That detail makes the Sun's future feel less quiet. After the planetary nebula fades, after the white dwarf remains, small bodies could continue to be perturbed onto dangerous paths. Asteroids might drift inward and be torn apart by tidal forces. Dusty rings could form around the white dwarf. Pieces of old planets could rain down onto the remnant. The star's corpse might carry chemical fingerprints of the worlds that once orbited it. A future astronomer around another star, studying the Sun as a white dwarf, might not see Earth. They might not know our oceans or cities ever existed, but by analyzing the white dwarf's atmosphere, they might detect traces of rocky material, calcium, iron, magnesium, and silicon, the ingredients of rocky planets. They might conclude that this dead star once had a rocky system that could be the last detectable evidence of Earth. Not a photograph, not a monument, not a signal, a slight chemical pollution in the atmosphere of a fading white dwarf. This is one of the most unsettling parts of the story. Planetary systems can leave fossils, but they are not fossils in stone. They are dynamical remains, scattered debris, altered orbits, and spectral lines in the light of a dead star. The Sun's death would turn the solar system into an astronomical crime scene, with clues spread across cold distances. Over longer timescales, even those clues would change. The white dwarf would cool slowly, very slowly. It would take billions and then trillions of years to fade from white to yellowish, from yellowish to red, from red to almost invisible infrared darkness. The exact cooling depends on its mass, composition, and atmosphere, but the direction is simple. It loses heat. It cannot replace that heat with fusion. It becomes dimmer and colder. Eventually, in the far future, a white dwarf is expected to become a black dwarf, a cold remnant that emits almost no light. But no black dwarfs exist yet. The universe is not old enough. White dwarfs cool so slowly that even the oldest ones still have some warmth. A true black dwarf would require a timescale longer than the current age of the cosmos. That means the Sun's final form is not something the universe has had time to produce anywhere yet. at least not from ordinary stellar evolution. The future contains objects that have never existed before. That thought changes the way we think about time. We often imagine the universe as ancient, and it is. 13.8 billion years is far beyond human intuition, but in the full life cycle of stars and remnants, the universe is still young. The age of black dwarfs lies ahead. The long cooling of white dwarfs belongs to a future so vast that our present cosmic era is only an early chapter. The sun's death will happen billions of years from now, but even that is early compared with the final cooling of its remnant. By then, the Milky Way itself will also be different. Long before the sun becomes a black dwarf, our galaxy will merge with the Andromeda Galaxy. The collision will not be like two solid objects smashing together. Stars are so far apart that direct stellar collisions will be rare, but gravity will reshape everything. Spiral arms will distort, gas clouds will be compressed, new stars may form. The two galaxies will eventually settle into a larger elliptical-like system sometimes called Milkomeda or Milkdromeda in popular descriptions. The sun, near the end of its life or already transformed, depending on the exact timeline, will be part of that changing galactic environment. This means the solar system's future is not isolated from the galaxy. Passing stars, galactic tides, and a rearranged gravitational field can disturb the outer Oort cloud. Comets may be sent inward or stripped away. The distant boundary of the sun's gravitational influence will become less stable over immense time. The sun will die inside a galaxy that is also evolving. Nothing in space is truly frozen into its present arrangement. Stars age, galaxies merge, orbits drift, clouds collapse, remnants cool. Even if a planet survives its star's death, it remains part of a moving gravitational system. The sun's white dwarf will continue orbiting the center of the Milky Way's future remnant. It may pass near other stars. Its surviving planets may be disturbed over trillions of years. Some bodies may be ejected, others may collide. A planetary system that looks stable over millions of years can become unpredictable over cosmic time. So when we ask what happens when the sun finally dies, the answer extends far beyond the moment of death. The death is a transition. The consequences continue. There is the immediate future, where Earth loses habitability long before the sun reaches its final stage. There is the red giant era, where the inner solar system is burned, swallowed, or left as scorched debris. There is the helium-burning chapter, where the sun stabilizes briefly as an elderly giant. There is the asymptotic giant branch, where the star pulses and sheds its body. There is the planetary nebula, where the lost outer layers glow. There is the white dwarf, where the core remains. Then, there is the long cooling, the fading, and the almost endless dark. Each stage answers a different version of the question. If you mean when the sun stops supporting life on Earth, the answer comes much earlier than most people imagine. The planet becomes unlivable long before the sun physically dies. If you mean when the sun stops being a normal star, the answer comes when hydrogen fusion in the core ends and the red giant transformation begins. If you mean when the sun loses its outer body, the answer is the planetary nebula phase. If you mean when the sun becomes a stellar corpse, the answer is the white dwarf. If you mean when the last faint warmth disappears, the answer stretches into a future so distant that the universe itself will be older than we can comfortably describe. That is why the title of this story is almost deceptive. The sun does not finally die in one moment. It dies in layers. First, it kills the world that depends on it. Then it stops being the star we know. Then it expands. Then it sheds. Then it remains. Then it cools. The death of a star is not a single door closing. It is a corridor of endings. For humanity, the most urgent part is not the white dwarf. It is not the planetary nebula. It is not the far future black dwarf that will not appear for unimaginable ages. The part that matters most is the gradual brightening of the sun over the next billion years or so, because that is the chapter that changes Earth. By the time the sun becomes a red giant, any civilization descended from Earth would need to have left the planet long before, not during the final swelling, not in a desperate last century, but far earlier. The timescale is vast, but the challenge is also vast. Moving a species, preserving life, or creating habitats beyond Earth would require technology, stability, and foresight on a scale we do not yet possess. Maybe future life will move outward. Maybe habitats will be built around Mars, the moons of Jupiter, the moons of Saturn, or free-floating structures in space. Maybe future civilizations will use the changing sun as an energy source for as long as possible, migrating as the habitable zone shifts. Maybe they will leave the solar system entirely, heading toward younger stars with longer futures. Or maybe there will be no one left by then. The sun's timeline is generous compared with human history, but it is not a promise. A billion years is enough time for continents to rearrange, climates to transform, species to rise and vanish, and intelligence to change beyond recognition. We do not know whether humanity or any descendant of Earth life will witness the sun's final phases, but the physics will happen either way. The sun does not need observers to age. This is one of the hardest truths in astronomy. The universe is not dramatic because it performs for us. It is dramatic because the processes are real whether anyone watches them or not. Stars are born in darkness. They ignite, they shine, they alter the worlds around them. They die. Their remnants cool. The story goes on with or without minds to narrate it. And yet, right now, there are minds able to understand the sun's future. We can calculate how hydrogen fusion changes the core. We can observe red giants and white dwarfs elsewhere in the galaxy. We can see planetary nebulae that show us what sun-like stars become. We can study polluted white dwarfs and learn that planetary systems can survive, break apart, and fall into stellar remnants. We can use other stars as previews of our own star's ending. The future of the sun is not a prophecy in the mystical sense. It is a scientific reconstruction, based on physics and observation. Every red giant in the sky is a reminder. Every planetary nebula is a clue. Every white dwarf is a fossil of a star that once had a long, bright life. When we look at them, we are not just looking at exotic objects. We are looking at possible chapters from our own solar system's future. Consider a planetary nebula, like the Ring Nebula or the Helix Nebula. Through a telescope, these objects can look delicate, almost peaceful. A glowing ring, a soft shell, a cosmic eye, but their beauty comes from loss. A star expelled its outer layers, a core was exposed. A long stellar life ended in a luminous cloud. One day, something like that may mark the place where the sun used to be. It might not look exactly like those famous nebulae. The shape depends on many details: rotation, magnetic fields, mass loss, interactions with planets, and internal waves can influence the final structure. The sun may create a faint or modest nebula compared with some dramatic examples. Scientists still debate aspects of how visible the sun's planetary nebula will be, but the general story remains. Outer layers leave, core remains, gas expands, light fades. That fading is important. The planetary nebula is not the sun's permanent memorial. It is a temporary display, lasting only a short time on cosmic scales. Eventually, the gas will dilute into space. Its atoms will become indistinguishable from the wider interstellar medium. The white dwarf will continue cooling alone. The final remnant of the sun will be small. That feels almost wrong. The object that dominates our sky, holds the planets, powers life, and contains almost all the mass in the solar system, will end as something roughly Earth-sized. The sun's huge influence will collapse into a compact point of dense matter. Its gravitational field will still matter, but its warmth will shrink to a fading glow. A future visitor approaching the solar system after the nebula fades would not see a yellow sun. They would see a dim white point. Around it, perhaps, distant giant planets, cold moons, debris, and dust, all inside a system still moving but no longer alive in the way it once was. If that visitor knew where to look, they might find the orbit where Earth used to be. Maybe there would be a surviving rock. Maybe there would be nothing recognizable. Maybe the inner solar system would be a ring of debris. Whatever remains, it would not tell the story easily. The oceans would not be there. The blue color would be gone. The atmosphere that scattered sunlight into a daytime sky would be absent or transformed. No clouds would drift across the surface. No forests would reflect green light. No city lights would outline continents. The death of the sun is also the death of Earth as a visible living world. That does not mean the universe becomes meaningless. It means life depends on temporary conditions. Every habitable planet lives inside a window. The window can be long. On Earth, it has lasted billions of years, but it opens, changes, and eventually closes. A stable star is not eternal. A habitable zone is not fixed. A planet that is perfect in one era can become impossible in another. This is the deeper lesson hidden inside the sun's future. Habitability is not just a place. It is a time. Earth is habitable now because the sun is at the right stage. Earth is at the right distance. The atmosphere has the right properties, and geological and biological systems have maintained conditions within a narrow range. Shift any of those pieces enough, and the same planet becomes hostile. The sun's death reveals that even the most familiar world is not permanently safe. But it also reveals something constructive. The atoms in our bodies came from earlier stars. The sun formed from material enriched by past stellar generations. Earth exists because previous stars lived and died before the solar system was born. The death of stars is part of the reason rocky planets can exist at all. Without stellar death, there would be no carbon for life, no oxygen for water, no silicon for rocks, no iron for planetary cores. The universe after the Big Bang began mostly with hydrogen, helium, and a little lithium. The richer chemistry required for planets and biology came from stars. Our sun will not create the heaviest elements, but it participates in the same recycling process. It formed from old material. It shines for billions of years. It creates some new elements in its interior. It returns part of itself to space. It leaves behind a remnant. It becomes one event in a much larger cosmic circulation. From that view, the sun's death is not only an ending, it is also a transfer. Energy has been flowing from the sun to Earth for billions of years. Later, matter will flow from the sun back into space. The star that gathered gas into itself will release gas again. What was once concentrated becomes diffuse. What was once a sphere becomes a cloud. What was once a cloud may eventually become part of another sphere. The universe builds by losing. That is not a comforting sentence in the ordinary human sense. It does not save Earth. It does not preserve the present. But it explains why endings in astronomy are often connected to beginnings elsewhere. Still, the future solar system will be quiet. The white dwarf sun will cool across enormous spans of time. Its planets, if they remain, will circle in darkness. Jupiter will no longer shine by reflected sunlight in the same bright way. Saturn's rings, if they survive at all, would be dim and cold. Uranus and Neptune would drift under a faint remnant. The distant comets of the Oort cloud would move through a weakened gravitational empire. Occasionally, something dramatic might happen. A passing star could disturb distant bodies. A comet could fall inward toward the white dwarf. An asteroid could be torn apart and form a dusty ring. A surviving planet's orbit could slowly change through gravitational interactions, but these would be rare events, separated by long stretches of stillness. The solar system would become an old machine running down, not broken in a sudden way, not frozen into total immobility, but deprived of the central furnace that once made it bright. Over time, the sun's white dwarf would become harder and harder to see. A young white dwarf can be hot and luminous. An old one becomes faint. At immense ages, it would radiate mostly at low energies. It would be a dense, dark object with only gravity to announce its presence. If black dwarfs eventually exist, they will be among the coldest stellar remnants. They will not glow visibly. They will not warm planets. They will be the final cooling stage of stars like the sun, after time has drained away their remaining heat. But by then, the universe will have changed in ways that make the sun's story only one thread in a much darker fabric. Star formation will slow as gas is used up or locked away. The brightest stars will die quickly. Smaller red dwarfs will keep burning far longer than the sun, some for trillions of years. White dwarfs, neutron stars, black holes, and cold planets will become more common than living stars. The cosmos will gradually shift from an age of light to an age of remnants. The sun's death is part of that universal movement. It is not unusual. It is not a cosmic error. It is what stars of its mass do. That may be the most sobering part. Our star is special to us, but not special to physics. Across the galaxy, countless sun-like stars have already gone through similar endings. Others are doing so now. Many more will do so in the future. The sky contains the sun's fate, repeated in different places and at different times. Some stars are still young and blue-white, burning fast. Some are orange and steady. Some are swollen red giants. Some have already shed nebulae. Some are white dwarfs cooling in silence. When we look at the night sky, we are not seeing one age of stars. We are seeing a population spread across life stages. The sun is simply one member of that population. It happens to be our member. That is why its death feels different. A red giant in a distant constellation is an astronomical object. The sun as a red giant is the end of the world that made us. A white dwarf in a telescope is a compact remnant. The sun as a white dwarf is the final state of the star that lit every human day. Science can explain the process, but it cannot remove the emotional weight of the idea. One day, there will be no sunrise on Earth. Not because of clouds, not because of an eclipse, not because a rotation stops for a moment, but because the relationship between Earth and sun will have ended. Either Earth will be gone, or it will be a dead world under a star that no longer shines as our sun. That is the simple truth beneath the long astrophysics. The sun is temporary. The current solar system is temporary. But temporary does not mean short. It does not mean accidental. It does not mean worthless. The lifetime of the sun is vast enough to allow planets to form, oceans to stabilize, life to emerge, intelligence to appear, and beings like us to ask how it all ends. In a universe where many stars live fast and die violently, our sun has been patient. It gave Earth time. That time is the reason every mountain, every ocean, every fossil, every language, every telescope, and every question exists. When the sun finally dies, it will not erase the fact that it once made all of this possible. It will erase the conditions that allow it to continue. There is a difference. The light arrived, the oceans existed, life grew, minds appeared. The future can close the chapter, and the closing chapter is written in stellar physics. The core exhausts, hydrogen, the star expands, helium ignites, the core changes, the outer layers pulse, mass escapes, a nebula glows, a white dwarf remains, the remnant cools, the solar system darkens. Step by step, the sun becomes less like the star we know and more like the remnants we observe elsewhere. If you want to imagine the final view, do not picture the sun exploding. Picture a dim point of white light in a cold system. Picture giant planets moving slowly in widened orbits. Picture dead moons under faint illumination. Picture debris occasionally falling toward the remnant, leaving chemical traces in its atmosphere. Picture the place where Earth once was, either empty, scorched, or gone. Picture a star that once filled the daytime sky, reduced to an ember smaller than the world it warmed. That is what happens when the sun finally dies. The solar system does not instantly vanish. The planets do not all explode. The galaxy does not notice in any dramatic way. But for Earth, and for everything that ever depended on the sun's steady light, it is the end of the only environment we have ever known. And perhaps that is why this future feels so strange. It is both enormous and personal. It is billions of years away, yet it concerns the star outside our window. It belongs to astrophysics, but also to every sunrise we have ever seen. The sun's death is not just a future event in space. It is the reminder that even the most reliable light in our lives is part of a longer story, a story that began before Earth existed, a story that made Earth possible, a story that will continue after Earth is changed beyond recognition. And when the final white dwarf cools in the dark, the sun will no longer be a star in the way we understand that word now. It will be a remnant, a dense memory of fire, a silent center of a colder solar system. The light that once made days, seasons, oceans, weather, forests, and eyes will have faded into the long night of cosmic time. There is another detail that makes this future even stranger. The sun's death will also change the meaning of distance. Today, the planets are arranged around a star whose gravity and light both matter. Earth is close enough to receive strong sunlight. Jupiter is far enough to remain cold but still bright in reflected light. Neptune receives only a tiny fraction of the sunlight Earth receives. Yet, even Neptune is still part of a solar system centered on an active star. After the sun becomes a white dwarf, that familiar map loses its emotional scale. A planet's distance will still determine its orbit, but it will no longer determine life in the way it once did. Being one astronomical unit from a white dwarf will not mean what it means around the present sun. The old Earth distance will not be the comfortable place between freezing and boiling. It will be a cold orbit around a tiny remnant. The habitable zone, if it exists at all, would sit very close to the white dwarf. It would be squeezed inward, near the remnant, not spread around the old orbit of Earth. A world there would complete an orbit quickly. Its sky would look nothing like ours. The star would be small, intense, and strange, a brilliant bead rather than a broad disk. If the planet were tidally locked, one hemisphere might face that light forever, while the other remained in permanent night. That kind of world could exist around some white dwarfs. Scientists search for planets and debris around stellar remnants because they reveal what survives after stars change. But in our solar system, the old inner planets would probably not be ready-made homes waiting beside the white dwarf. The violence of the red giant phase would have already done too much damage. This turns the sun's death into a lesson about timing as much as location. A world can be at the right distance during one era and the wrong distance later. Mars may be too cold today, briefly less cold under a swollen sun, and then frozen again around a white dwarf. A moon in the outer solar system may experience a short interval of extra sunlight, then return to darkness. Even the most promising frozen ocean worlds would not escape the larger truth that the star around them is changing. The solar system's future is not a single apocalypse. It is a moving target. Every orbit that once seemed permanent becomes part of a shifting environment. Radiation changes. Gravity changes. The star's size changes. The balance that defines a planet's surface can disappear without the planet itself being destroyed. That is why Earth's fate is so haunting. The planet does not need to be shattered to be lost. It only needs the conditions that make it Earth to end. Remove the oceans, and Earth becomes something else. Strip the atmosphere, and the sky disappears. Bake the crust, and the surface loses its memory of biology. Change the sun enough, and our planet remains only in name. There is also the question of what happens to the moon. If Earth survives the red giant phase, the moon may continue orbiting it for some time, though the Earth-Moon system would be altered by tides, solar mass loss, and the long-term evolution of its orbit. But the moon's familiar role would be gone. It would no longer shine over living seas. It would no longer pull tides through oceans. It would no longer mark calendars for creatures watching from the ground. The moon would become a companion to a dead or ruined world. That detail may seem small compared with the death of the sun, but it shows how deeply the sun's future reaches into everything we recognize. The sun does not only provide light, it gives meaning to the relationships among bodies in the solar system. The moon is beautiful to us partly because sunlight gives it phases. Mars is red in our sky because sunlight reflects from its dusty surface. Saturn's rings glow because the sun illuminates ice. Comets grow tails because solar radiation wakes them. When the sun changes, the whole visual language of the solar system changes with it. Even shadows would not be the same. A red giant sun would cast a different kind of light, redder and more diffuse from a much larger surface. A white dwarf would cast sharper, weaker, stranger illumination. The planets would not merely occupy new thermal conditions. They would live under a different sky. Then, there is the effect on time itself, at least the time kept by worlds. Today, Earth's day and year shape the rhythms of life. Seasons come from the planet's tilt and its orbit around a stable sun. Calendars follow a predictable relationship between rotation, orbit, and light. In the far future, if Earth survives, a year may lengthen as the sun loses mass and Earth's orbit expands. A day may continue changing slowly through tidal interactions, but the biological meaning of those cycles would be gone. A calendar without life is only motion. The same is true for the outer worlds. Jupiter's moons will continue their orbital dances. Io may still be tormented by tidal heating as long as its resonances persist. Europa may still hide an ocean if internal heating remains enough. Enceladus may or may not continue venting depending on Saturn's system and its own evolution. These are not simple questions because moons depend on gravity as much as sunlight. That makes the outer solar system one of the more complicated parts of the sun's death. Close to the sun, the story is brutal and direct. Too much heat, too much expansion, too much loss. Farther out, the story becomes more subtle. Some bodies receive more sunlight during the red giant era, then lose it. Some internal oceans might outlast surface warmth. Some chemical processes might accelerate briefly and then stop. Some moons may remain geologically interesting long after Earth is sterile. If any life existed beneath ice, it might not care much about sunlight at first. Life around hydrothermal vents on Earth shows that sunlight is not the only possible energy source. Chemical energy from a planet or moon's interior can support ecosystems. That idea is why icy moons are so fascinating today. If something similar existed on Europa or Enceladus, the death of the sun would not necessarily end it immediately. But long-term survival would still depend on internal heat, tidal relationships, and chemistry. The sun's death would remove one important source of energy and alter the gravitational layout of the system. It would not make hidden oceans impossible, but it would change the context around them. This is why the final solar system may not be completely dead in every possible sense. It may contain pockets of activity, a cooling white dwarf at the center, gas dispersing into space. dust rings from shattered asteroids, giant planets still radiating leftover heat from their interiors, moons with buried oceans or frozen chemistry, comets falling inward after being disturbed by distant gravity. The scene is not lively like the present solar system, but it is not perfectly still. Dead stars can still have dynamic surroundings. Remnants can still shape orbits. Debris can still collide. Gravity continues long after warmth fades. This distinction matters because space rarely gives us clean endings. It gives us remains. The present Earth contains remains of earlier worlds and stars. Meteorites carry records from the beginning of the solar system. Craters preserve impacts. Isotopes reveal ancient processes. In the future, the post-sun solar system will also contain records, though not necessarily records anyone can read. Some fragments of Earth, if ejected before or during the sun's transformation, might wander through space. Some material from the solar system may be thrown into interstellar space by gravitational encounters. Tiny pieces of what once orbited the sun could drift between stars for immense lengths of time. In that sense, the solar system may leave behind more than a white dwarf. It may leave wanderers, cold rocks, grains of dust, metal-rich fragments, frozen bodies detached from their original home. Matter that once belonged to our neighborhood could become interstellar debris, moving through the galaxy without any memory of the star it came from. This is not fantasy. We already know that interstellar objects can pass through solar systems. Objects like Oumuamua and Borisov showed us that material can travel between stars. In the far future, the dying sun and the disturbed gravity of the evolving galaxy could help release some solar system material into the wider Milky Way. Perhaps, long after Earth is gone, a fragment from our system could pass through another planetary system. It would not announce itself as a relic of oceans and life. It would be just another rock, another icy body, another piece of cosmic debris. But its atoms would have a history. They would have once belonged to a system where a yellow star shone over a living planet. That is a quiet kind of survival, but not the survival we usually want. We want continuity. The universe offers transformation. We want preservation. The universe often provides recycling. We want the story to remain readable. Cosmic time turns pages into dust. The sun's death shows all of this without needing a supernova. It shows that ordinary stars are powerful enough to erase their own worlds, gentle enough to do it slowly, and important enough to create the conditions for new systems later. There is also a final irony in the sun's future. The star that made Earth bright will end as an object astronomers study best in faintness. White dwarfs are detected by their dim light, their color, their spectra, their gravitational effects, and sometimes by the debris around them. They are not showy like red giants. They do not dominate star-forming regions like massive young stars. They are subtle, compact, and quiet. Yet they are among the most important clocks in astronomy. Because white dwarfs cool predictably, scientists can use them to estimate the ages of stellar populations. In clusters, the faintest white dwarfs help reveal how long the cluster has existed. A dead star becomes a clock. One day, the sun will be such a clock. Not for us, most likely. Not for Earth. But in principle, a future observer could estimate how long ago the sun left its giant phases by measuring the cooling of its white dwarf. The remnant would not speak, but its temperature would carry time inside it. That is one of the strangest things about stellar death. The star loses its active life, yet becomes a record of time. The white dwarf sun would remember its own cooling through physics. The debris around it would remember planets through chemistry. The expanded orbits would remember mass loss through dynamics. The absence of Earth as a living world would remember the end of habitability through silence. Astronomy reads those kinds of records all the time. It does not need inscriptions. It reads light, motion, temperature, composition, and structure. The universe writes in physical consequences, so the sun's final story would still be written, even if no one from Earth remained to read it. That possibility is lonely, but it is also honest. The cosmos does not guarantee witnesses. It only leaves evidence. For now, we are the witnesses. We live before the oceans are gone, before the red giant, before the planetary nebula, before the white dwarf, before the long cooling. We live in the rare middle of the sun's stable life, when its light is strong enough to sustain a biosphere, but not yet strong enough to erase it. That is the narrow chapter from which we are able to look forward and understand the ending. And because we understand it, the present sun becomes more than a bright object in the sky. It becomes a stage in a stellar life cycle. Every sunrise is not only a beginning of a day, but evidence of a temporary balance between gravity and fusion. Every sunset is not a sign that the sun is failing, but a reminder that Earth is rotating under a star with a finite future. The sun feels eternal because human lives are short. Astronomy tells us that eternity is not the right word. Stability is not